Okay, good afternoon and welcome from Ottawa. My name is Professor Henry Sari and I am an associate professor at Carleton University in the Department of Mechanical and Aerospace Engineering, and I will be presenting parts 3 and 4 of this particular tutorial. And so now we'll start looking at materials for sCO2 power cycles. In terms of a brief outline for this particular presentation, I will introduce you to some of the basic operating conditions and material requirements for steam turbines, gas turbines, as well as sCO2 power cycles. We'll identify some of the material technical challenges and the knowledge gaps in those technical challenges that we've identified. And then we'll specifically start looking at the behavior of materials in CO2 and sCO2 environments, looking at previous experience, summarizing some of the sCO2 corrosion testing that's been done, and then highlight some of the current and planned testing that is underway to address the various gaps that we identify in this tutorial. So if we look at this slide here, this slide essentially shows us a comparison of a gas turbine, which is a 100 megawatt GE frame type gas turbine, a steam turbine, which is this sort of well-known historical unit of approximately 100 megawatts output as well. And not shown on this slide, but we also have a comparison with an sCO2 Brayton cycle that was nominally 100 megawatts and operating at a turbine inlet temperature of approximately 700 or 750 degrees C that was partially designed at Carleton University by various fourth-year project students. So we have plots showing temperature, pressure, and density of the working fluid passing through the cycle. And we see that the gas turbine has the highest maximum temperature in the cycle, and that it doesn't have, in the open cycle arrangement anyway, it doesn't have a cooling section. Rather, the exhaust gas is just exhausted into the atmosphere. For the sCO2 Brayton cycle and the steam cycle, the maximum temperatures seen in these cycles are approximately similar, but in the steam cycle, where the expansion and the cooling occurs, there is quite a large drop in temperature from the maximum to the minimum in the cycle. Whereas in the sCO2 cycle, we see that there's not as large of a drop during the expansion process in the turbine. And then like the steam cycle, we have an additional cooling phase where we bring that temperature back to the turbine inlet temperature. In terms of pressure, we see that, at least in this case, the steam cycle has the highest pressure. The sCO2 cycle is comparable to the steam cycle. And then the gas turbine has quite a low absolute pressure in the cycle. In terms of the densities, the density of the gas in the gas turbine cycle doesn't really show up. The density of the sCO2, in that it doesn't go through any phase changes. For the most part, it's a single phase in the supercritical regime, and the density stays relatively high, and it's intermediate between the low gas density and the high density, for example, when we have water. When we generate the steam and then expand that, obviously the density goes down quite a bit, and then in the cooling cycle in the steam turbine, we get quite a large change in the density. Now, all that being said, the sCO2 Brayton cycle is kind of an intermediate, let's call it, between a traditional air-breathing gas turbine and a steam turbine. And when we look at some of the components moving forward and some of the design requirements, we'll also notice that the sCO2 Brayton cycle and the various equipment that goes along with it are kind of a mix between the gas turbine and the steam turbine. So if we look at steam turbine requirements and materials, we'll go through this relatively quickly. There's kind of a small range of materials that you can choose from for steam turbines, and some of the main requirements that you're looking for are a good match of thermal properties for the different materials that come into contact. These are relatively large components, so changes in temperature could result in large deflections and distortions. So we want to try to match those thermal properties between the different materials. And again, because we're usually talking about relatively large equipment, we're looking for high temperature strength for operation at those high temperatures and acceptable cost to keep the capital cost of the plant down as much as possible. So the main components for a steam turbine would be, for example, the turbine casing and the shell, shown here and here, the bolting to keep the top and the bottom casing together, the rotors and the discs, and then the aerodynamic vanes and the blades as well that are either attached to the casing or attached to the rotors and discs. In terms of materials, there's just a general outline here in terms of the different main components and what sorts of materials you might see, such as 9 chrome and 12 chrome steels or nickel-based alloys, depending on the specific component, as well as a few other things that you're looking for, like high temperature creep strength, castability, and weldability, obviously for the casing and shells. For the rotors and discs, looking for high creep strength, forgeability, and weldability to help process those components. In terms of gas turbine requirements and materials, to some degree they depend on whether or not you're talking about an aero engine or an aeroderivative engine for industrial applications, or a frame type engine. In terms of the aero engines and the aeroderivative engines, you're going to have more lightweight, to some degree, perhaps more exotic materials making up the gas turbine and its various components. You're going to have roller bearings supporting the various shafting in the turbine, that sort of thing. Coatings are going to be very important, especially in the high temperature stages of the engine, as well as in the most modern engines. You're going to have internal blade cooling to allow the blades to operate, and that works in conjunction with various coatings that you would apply onto the turbine blades and vanes. The industrial gas turbines are going to be, in general, of a heavier structural build with larger, beefier components and sections and combustors, and usually using hydrodynamic oil lubricated bearings to support the shaft. More modern engines will make use of some of the aero engine technology that trickles down into the industrial engines in terms of the directionally solidified and single crystal alloys, as well as the coatings on those materials and components. So now, before we take a look at an example of an sCO2 Brayton cycle and what components are involved in there, we can look at this table relatively briefly. And this goes back to the reference case that was mentioned earlier in the tutorial, but we can also apply it to various other sCO2 Brayton cycles as well. We've got various components broken up into heat exchangers, the turbomachinery components, balance of plant components, including valves and piping. So you've got the various components or subcomponents within those groups. We've got the material types that have been studied for application for these components, the supporting technical base or technology base for those materials, and sort of the current risk or rationale for using those materials for those components. And if you glance through this table, you can see that for many of the components, material types, if not specific material grades, have been identified for the various components, and the supporting technology base either coming from gas turbines or steam turbines or other industries such as the nuclear industry. There is a relatively large supporting technology base there. Now, whether or not that supporting technology base is sort of 100% ready to go for sCO2 Brayton cycles, that's a little bit more of a pressing question. And we see that depending on the component, the materials and the technology is ready to go, or it's at sort of a much lower technology level to be used for some of the components. So taking this into account, there are quite a few gaps still in terms of selecting and using materials for sCO2 Brayton cycles, and we'll start to look at those in just a very short while. But before we do that, we'll just spend a little bit of time on this slide. And this slide is an overview of the 10 megawatt step facility and some of the components within that step facility. And I just want to highlight some of the materials that are used for some of these components, as well as relating that back to what we saw previously in this tutorial on the work that's been done on the AUSC material development. So this plot or this figure here shows the overall step facility equipment arrangement. You can see that it's relatively large in relation to the Turbomachinery. And just one thing before we move on, I forgot to mention when we compared the gas turbine, the steam turbine, looking at the pictures of the two examples, the gas turbine on that slide was essentially, for all intents and purposes, the entire power generation unit, whereas with the steam turbine, that was only the turbine, the casing, and the generator itself, and it did not include all the other equipment that you would see in a steam power plant, such as the coal handling equipment, the combustors, the boilers, the piping, the heat exchangers, the condenser, and the exhaust system components in there, and that would be much larger than that Turbomachinery that was shown on that slide. So the same sort of thing is evident here, where the Turbomachinery, when we talk about, in this case, the turbine with the bypass compressor being hidden in here, and then the main compressor driven by a variable frequency drive shown here. We have various other components that are spaced out in the plant assembly. So for example, the process heater to put the heat into the cycle, the chillers, and the cooling tower to remove the heat, the piping, and the various other heat exchangers that transfer heat within the cycle itself. So this plant, though it's for only a 10 megawatt power output, it's relatively large and spacious, but one of the reasons for doing that is to provide for flexibility and future rearrangement of components and addition of components and rearranging the Turbomachinery and the cycle components themselves to be able to test other various cycle arrangements, that sort of thing. So this is the overall arrangement. If we look at kind of a top view here of where the turbine and the compressor skid live, as well as some of the recuperators, we can see the piping arrangement and some of the piping materials that were selected for this system. So in red, we have pipes that are made out of the Inconel 740H material that was developed as part of the AUSC program. And then we have blue pipes in the colder section of the cycle that are more of a more standard P91 material here. In terms of some of the components that are in here, so for example, we've got the low temperature recuperator. We've got high temperature recuperator hiding in there as well. And if we look at the material for at least the high temperature recuperator, that's going to be a 316 stainless steel that was selected for that. It has a high enough temperature capability, and it doesn't get into the more exotic heat exchanger materials that you might be involved with at higher temperatures. The turbine, which lives right in here. There's a cross section shown here, and we can see that it's quite reminiscent of the steam turbine casing, where you have relatively heavy, thick sections. But then when you look at the rotor and some of the turbine blades on that rotor, at least the turbine blades are a little bit more reminiscent of what you might see in a gas turbine engine. So again, you've got a bit of an overlap between the steam turbine and the gas turbine when you're looking at the components and the design of those components. The step turbine rotor, it's machined out of a monolithic mnemonic 105 forging, and it's EDM to get the blade shapes and the blade profiles within that turbine rotor. The step turbine stop valve, which is located here and here in the facility arrangements, that or the body of that stop valve was cast out of Haynes 282, and again, that's one of the new materials that was just recently code qualified, and quite a long process in doing that. But again, that previous work has ensured that materials are available for these sCO2 pilot plants and other such plants, so that the material is there for components to be designed from and made, and at least for a lot of the components, the availability of those materials is there as well. So now if we start kind of getting into the materials technical challenges that we've identified, this slide highlights them all, and it kind of breaks it up into two, I guess, and maybe the timeline or the terminology for the knowledge and the gaps is perhaps a little bit dated now. But when I talk about current knowledge, what I'm talking about there is existing materials being available with known mechanical properties. And for the most part, as we saw a couple slides ago, this material and mechanical property database is pretty good for the main components, the piping, the valves, the turbomachinery components, that sort of thing. On the environmental consideration side of things, where we're talking about the compatibility of the materials with high temperature and perhaps slightly lower temperature supercritical CO2 as well, quite a bit of corrosion testing has been done over the last 10 years or so. And sort of corrosion and the material compatibility of materials in sCO2 was identified quite a while ago as one of the sort of important technical challenges to be overcome. And I think even though all the work is not completely summarized in this presentation, I think for the most part, and I don't want to say it too strongly, leave myself a little bit of wiggle room there, but I think for the most part, the compatibility of materials in sCO2 has been sort of sussed out. But regardless, that those studies are still relatively short term, have been made with coupons for the most part, rather than real components and that sort of thing. The representative temperatures and pressures that we would see in various sCO2 cycles have been covered by the testing, and the results for the most part have been presented as mass gain versus actual corrosion penetration, that sort of thing. So we do have a pretty good idea of what's going on here, but even with some gaps here, some other gaps were identified, and various technical challenges associated with those. And we will touch on some of these technical gaps in terms of availability of materials, some more environmental considerations, the performance of actual components and material forms, and then a few other challenges and considerations that we've lumped in here. So again, sort of to summarize where we are now, materials are available, but gaps remain, and efforts are required to complete the picture. So this slide here is just a brief summary of the pressures and temperatures for various corrosion testing that has been performed. And we can see that they cover kind of the entire design space for perhaps the cold side of an sCO2 cycle, typical hot side of an sCO2 cycle, as well as some higher temperature cycles, so concentrated solar power cycles, direct fired fossil energy cycles, that sort of thing. So I think we've got a relatively good idea of what happens with materials under these conditions of pressure and temperature. And again, in terms of characterization, we've looked at weight gain. Some studies have shown corrosion layer thickness as well, and the scales and mechanisms of the corrosion has been covered there as well. In terms of the materials tested, again, they kind of cover the whole gamut of materials, so various steels, ferritic martensitic, austenitic, and nickel-based alloys as well. And what have the results told us? So I won't get into all the details, but just very generally, ferritic martensitic steels gain more weight than austenitic steels, gain more weight than nickel-based alloys. So essentially, the more chromium you have, or the more nickel and chromium you have, the more corrosion resistant your materials will be. So nothing too terribly surprising there. And when we look at the mass gains for sCO2 and steam, and again, these results aren't presented here, the mass gains for similar conditions are approximately similar. So that led people to think that maybe the scale morphologies in sCO2 would be plus minus similar to what's seen in steam under the same conditions, so that what people have learned from steam corrosion perhaps could apply to what's going on in sCO2 corrosion. And I think there's some evidence, some basis for evidence there. Just to go over the plots very quickly, we have the normalized weight gain, so milligrams per area. We have time from 0 to 3,000 hours, and these plots show the weight gain for various different alloys. So on this scale, you'll notice it goes from 0 to 12. So we can kind of see the 12 chrome at high temperatures. The other guys perform relatively well, either at that temperature or lower, depending on the material. If we blow up this part of the chart, we see something like this, where the 12 chrome at 400 degrees is maybe performing a little bit better than the 316 at 650 degrees. So you can kind of have a quick comparison there. And then these other alloys perform even better. And if we blow up that, now our scale goes from 0 to 0.4 or thereabouts. And we can see that we've got, for example, the 310 stainless steel here, 800H, and then 230 and 625 at those relatively high temperatures. So just to give you a sense of what's going on there. And then again, to summarize the main findings here, alloys with high chromium and nickel, and depending on the conditions, titanium and aluminum are more corrosion resistant because they build a stable, tight oxide layer that resists corrosion. Alloys with lower chromium levels are less corrosion resistant, and we typically see duplex layers or duplex corrosion scales in those alloys that don't resist corrosion as well. And again, some of the simple things here: increased corrosion with temperature, and to some degree this is important here. There doesn't seem to be that much of a pressure effect. So testing at sort of lower pressures, ambient pressures of CO2 versus supercritical CO2 at high temperatures, they seem to be relatively similar in terms of the corrosion effects there. This is a plot from the Supercritical CO2 Fundamentals book, and this illustrates that if we set a metric for a given amount of corrosion layer growth, in this case less than 100 microns of oxide over a time period of 100,000 hours, we can sort of see what parabolic growth constant gives us or sort of reaches that limit or keeps us below that limit. So that parabolic growth constant is about 5 times 10 to the minus 13 for that 100 micron corrosion layer in 100,000 hours. So we can see that for the various alloys and the various temperatures that we might see those alloys in application. We can kind of get a sense for, from a corrosion perspective, how high of a temperature can we operate those alloys at. And then if we sort of come back to, maybe I'll just skip this one. And if we come back to this shingle decker chart, again, that showed us for operation at a given temperature, the minimum desired strength at that application temperature is given by this line. And so we can see that we've got materials that are available that provide the strength. But if we start looking at where are the temperature cutoffs for different materials when corrosion is considered, that sort of leads us to a slightly more interesting question and might limit the temperature use for some of those alloys. And it looks like Bruce Pint has a paper in this conference that looks at some of those aspects, and I look forward to seeing that. So if we look at for the steels, even though we can operate those steels maybe at a 620 degrees C from a mechanical property point of view, if we look at the corrosion results and what's going on there, maybe our temperature limit for that due to corrosion is a little bit lower. Same sort of thing for solid solution alloys for AUSC applications. They're designed to sort of run at 700 degrees C, but the corrosion limit for those might bump it down a little bit. And then same sort of thing for the age hardenable AUSC alloys that were designed for 760 degree operation. Maybe the corrosion limit has to drop down a little bit further. So if we revisit again the materials technical challenges, we kind of highlighted what was going on here. So if we revisit this box here, efforts are required to complete the picture and they are underway. Now we'll look at these other gaps and remaining technical challenges for the rest of the presentation. So in terms of availability, having code compliant materials and design codes and having the supply chain ready to go, I think we're in better and better shape there. The Inconel 740 code case was approved a number of years ago, and then just recently the Haynes 282 code case has been approved for use of Haynes 282 in the boiler and pressure vessel code. Design codes for valves and heat exchangers. I think there's more space for work to be done there. In terms of the supply chain, Inconel 740 and to some degree Haynes 282 seem to be available for different components and different stock components there. And again, there's a paper in this conference updating what's going on for Inconel 740. So again, another interesting paper to have a look at and to see where we stand for using Inconel 740 in these power plants. In terms of environmental considerations for use in high temperature sCO2, again, to some degree, or to the large extent, the testing has been short term, and if you look at what happens here at under longer term testing, you might have that protective oxidation layer break down after a certain period of time, and then after that breakaway of the protective corrosion layer, you get a much larger or much higher corrosion rate or weight gain after that breakaway, and that typically comes from carburization and internal oxidation leading to that breakaway corrosion or exfoliation. So depending on the material you have and the extent of internal oxidation and oxidation and carburization, that might be an important aspect to study further, and some relatively recent work has been done in that area. In terms of testing under real conditions, again, the testing for the most part has been done in static conditions under no stress to the component. Usually not too much in terms of impurities for the various closed cycles that we might see, as well as the direct cycles that we might see, in the impurities that we would see in the fluids in those cycles. There has been some work done, for example, on C-ring testing and testing of pipe materials where the corrosion specimen is the pipe itself. In terms of impurities, looking at research grade versus industrial grade sCO2, there doesn't seem to be that much of a difference, but open cycle conditions with all the various other additives that you might see in the CO2 then could provide for different results there. In terms of reliability of data, a number of years ago, a round robin testing program was started to look at how comparable and how reproducible the results are for different materials under different testing conditions and testing procedures. For example, furnaces, that sort of thing. Initial testing results from 2018 showed the corrosion results to be pretty much plus minus consistent, and some more later results from that round robin test are being presented in this symposium as well. Mechanical property degradation is something else that has to be looked at. So what happens to the ductility and the tensile properties, for example, of materials in sCO2 exposure, especially under long-term conditions. And again, people have been looking at that, and some results are presented in this conference as well. So if we look at actual components and materials forms, if we look at thin section properties, for example, and compare the microstructures and mechanical properties of those thin sections, they're not always the same as the thicker sections that we might see in other manufacturing processes, or those sections used for mechanical property testing. So people are looking at that, and again, some results are presented in this conference. What happens when we diffusion bond, braze, or weld these various materials? People have started to look at that, and again, some results of some of those analyses are presented recently, as well as in this symposium as well. Erosion, fouling, and of microchannel heat exchangers. Again, there was some evidence of erosion earlier on in some of the test loops, and is that a real problem or not, or was that coming from the fluid or from the debris or exfoliation? People have looked at that, and I think more or less answered the question there. Oxide scale itself may cause a blockage, so we have oxide scale growing within these microchannel heat exchangers. You can change the heat transfer properties of these heat exchangers, as well as fouling or plugging of the small passageways within those heat exchangers that could cause problems as well. Some of the final other challenges and considerations, some of which are addressed in this conference as well. Looking at cost-effective alloys, again, to keep the capital cost down, you want to be able to use the cheapest or the most cost-effective alloy that does the job. For higher temperature applications, such as the direct fired cycles, that sort of thing, people have started looking at some more exotic materials like silicon carbide piping. And Bruce Pint again is presenting in this conference for some material options for some of these higher temperature applications. People can perhaps look at coatings to allow the use of lower cost alloys with a coating on them, or in other words, to help push the corrosion limit of the material back up to where the structural limit was. Non-metallics are important, especially for seals and valves and that sort of thing. So what happens when those seal materials or polymers come in contact with sCO2, and what's the compatibility like there? I think there's room for a fair bit of work to be done there. And then the other bit that I mentioned earlier was being able to leverage some of that previous work. In other words, comparing the work that was done for steam cycles and supercritical water corrosion and pressure effects, and extending some of those models and the results of those studies to what's going on in supercritical CO2, and perhaps being able to extend some of those models to sCO2. Okay, so that brings us to the end of that portion of the presentation, and just in the interest of time here, I will go through this summary very, very quickly, because I think for the most part, again, it kind of highlights some of the gaps that we were talking about, and maybe brings up a few potential other issues. Let's see here. I think we've talked about most of that, or addressed it to some degree. This is an interesting one. So the high mass flows require quite large piping for the larger applications. So are standard pipes available, or do fabrication of custom pipes out of these more exotic materials need to be done? That's an interesting point that perhaps needs to be looked at. Kind of mentioned most of that there. And then again, just bringing us to a quick summary and recommendation here. Sort of the bottom line is that the work that was done on the AUSC studies has helped to make these sCO2 power plants a reality, and perhaps to some degree a more coordinated effort similar to that AUSC materials program is recommended to help address some of the gaps that still exist for these sCO2 power cycles and the components. Okay, so that brings us to the end of the presentation. Subu will be happy to address any questions or comments. If for any reason he can't answer them, you can email Steve or myself directly, and we can get back to you and help you out with those questions or comments that you might have. Okay, thank you for your attendance and your thanks again, and hopefully we'll see you in person at the next symposium or the next conference.